Thank you. Yeah, my name's Etienne, co-founder and CTO of Weaviate, the company that builds the vector database of the same name. And I want to talk to you about today about multi-tenancy. And that's a very, very specific topic in vector search. And it comes with its own challenges, it comes with its own solutions, but maybe first you're wondering, like, what does that even mean, or why should we care? So to set the scene, imagine that you have an app that lets you upload any kind of data that you have on your hard drive, and you can chat with it. So kind of like a mix of Dropbox and ChatGPT in a way. And if you have that kind of app, it's super powerful to chat with your own files, but what you definitely don't want is someone else to chat with your files. So for every user that's on that kind of platform, every user needs some kind of separation, and that user or user group would be a tenant in this case. And then if you're the vendor of that app, current solutions or previous solutions would make you pay for every single tenant that's currently onboarded onto your system. But maybe at a given point, only 5% of tenants would be active at the moment. So why should you pay for the other 95%? And when you build a vector database, which is sort of very fast evolving field and lots of stuff that's needed, sometimes it's hard to know what to focus on. But also, in these like rare cases, the stars kind of align, and it just becomes super obvious. And multi-tenancy for us was one of those scenarios. So our commercial customers started saying, like, hey, we really need strong isolation between our tenants. Like, we want to do GDPR, we want to be GDPR compliant, we want to do like SOC 2, we have all these security questionnaires that we need to answer, and like separation or isolation is a big requirement there. And then, of course, also cost reduction is always something that businesses are happy about, so that was also something that they needed. Very similar from an engineering perspective. So engineers said, well, I have millions, I have tens of thousands or even millions of tenants, and whatever is out there, it just can't handle the scale. Like, I need something that can actually handle the scale. And then the open source community, so Weaviate is open source, and we have a vibrant open source community. It's rare that sort of the commercial and the open source interests align perfectly, but exactly the same thing. We started seeing, like, on our forum and on our Slack, we started seeing the same thing coming up about multi-tenancy. By the way, you may have noticed the past 5 slides all had AI-generated images on there, and this one is my personal favorite. Like, the longer you look at it, the weirder it gets. Like, the person in the yellow shirt, like, is the hand is also kind of the keyboard. It's like all merged up. So this one's great. But yeah, back to multi-tenancy. Why did existing solutions, why were they not able to handle the scale? And for this, we need to talk about the workarounds that our users used to do, or that people out there used to do. And the first attempt that we still find in many documentations these days is the filter approach. So you would just, if you imagine sort of a SQL database, you would put everything in a single table, and then you would filter for your tenant at query time. So like it's represented by this, like, where tenant ID equals 1, 2, 3, 4, 5. And this has a couple of problems. So first of all, it has none of the good isolation stuff. So for the security questionnaire, not very helpful if you have a single giant table. But more importantly, it's also very, very inefficient. So vector databases typically use some kind of vector index. In Weaviate, we use HNSW, which is a very popular one. And HNSW is a proximity graph. So you connect every single object in the database. You create edges between them to connect it. But if you create that giant graph spanning every single tenant in the database, but you only ever query a tiny fraction of it, that is very inefficient. Like, both in the retrieval part, because the index serve was not designed to only be queried in parts. But also, like, why did you build this massive index in the first place if you only ever are interested in a tiny fraction of it in a single query? This also makes it super difficult to scale dynamically, because what do you do if your index grows? Like, if it grows larger than a single machine, like, the only thing that you can do basically is either you scale vertically, or you sort of split it up before into a fixed number of shards, because resharding with vector indexes is super expensive. So that makes it very difficult to scale dynamically. And then the last one, this is my personal favorite. So we had a user who launched their app on Product Hunt, and it was really nice. Like, lots of people signed up, and they had a free trial. And the trial ran for 2 weeks. So after those 2 weeks, couple of users were convinced, they converted into paying users, but also they were users that did not convert, and now they had to be dropped off from the system. And in vector indexes, and pretty much all vector indexes out there, a delete operation is often more expensive than a create or an insert operation. So now if you have, let's say, 90% of those users don't convert, all of a sudden, like just removing them from the system would affect those 10% that do convert. So kind of like your paying users that are staying with the system would be affected by the ones that need to be removed. Yeah, that's all pretty bad. The second sort of workaround would be to create one collection per tenant. So this was actually the recommended way in Weaviate before we had a multi-tenancy solution. And this is because it does give you some of those, like it does overcome some of those shortcomings. For example, you do have the strict isolation, because if you have one collection per tenant, that means every tenant is its own thing, which is good. So you have the isolation. You don't need the filter anymore, because sort of narrowing it down to the specific tenant, like you could name your collection after the tenant, and then you just specify the tenant name, and that gets you to the right collection. And it makes offboarding easier, because you have that kind of isolation. So typically, in most database systems, dropping an entire collection is cheaper than sort of removing individual rows from an existing collection. And it kind of scales well. So it has, like, because it's independent indexes or independent collections, that's at least easier to distribute it in a distributed system. That said, that's only kind of true in theory, because what we saw is that it does scale well for the data. So the data can be scheduled on different nodes, and that's kind of a typical use case. But now you have millions of collections in a system that was not designed to host millions of collections. So the schema part, which is basically the metadata of those collections, that did not scale at all. You do also get lots of duplication, because all of a sudden now, like let's say for each collection, you have a couple of properties, a couple of settings that define that collection. If you want to update one, and you have a million collections, now you have a million updates to do. So that's kind of cumbersome. And then another one, this one is maybe a bit specific to Weaviate. Again, a system that was not designed to hold millions of collections. So if it crashed and you need to recover, all of a sudden, like the recovery operation was not for one collection, but for a million, and then it took quite a long time. So really, all of this, these were the workarounds that everyone out there used, just because there was nothing better to do, but we really wanted to make it better. So we thought, let's tackle this problem for once and for all, and like let's really address it at the root. And for this, we set out with a couple of design goals, and the first one, the most obvious one, is just scale. We want to support millions of tenants in a single cluster. So that doesn't necessarily mean a single machine. This could be a distributed system, but it means that you shouldn't have to do any kind of workarounds where you sort of shard your setups, because a single setup can only handle, I don't know, 10,000 or so. It really should scale into the millions and beyond. We do want that strict separation, so for compliance sake, but also for technical reasons. And we do want linear scalability. So I think that is the most important one for me. It's very hard for your kind of application, it's very hard to predict how many users you're going to have 3 months from now. So if you run out of compute space in 3 months, what we want is to just throw compute at it, add more nodes to the cluster, but you definitely don't want to be in a situation where sort of a sizing decision that you took 3 months ago all of a sudden like holds you back from onboarding new users, which from a business perspective is exactly what you want. Resource isolation, so we talked about the sort of delete interfering with the other users kind of case, but also just in general, like hot users, like hotspots basically on the cluster, users that are queried very frequently, others that are queried infrequently, so you want to have some kind of control to separate this. And then also the cost reduction part that we haven't talked about yet, you shouldn't really have to pay for inactive users. So we knew that in this kind of setup, sharding would likely play a key role. And to understand why, we need to look at the previous example or the previous workaround that worked kind of well, where we created a single collection per tenant. And why did that work? Because under the hood, for every collection that we created, there was a shard in that collection. So the shard was really the point that gave us the isolation that gave us some of the good stuff with this workaround. So to understand sharding, basically this is the single tenancy situation. There would be some sort of an algorithm, so consistent hashing ring algorithm, which basically means if you get a key in, the key sort of falls in some of those buckets. The buckets then map to a virtual shard maps to a physical shard, and that would be eventually scheduled on a node. So it's basically sort of this way to, for the traffic to find the right way. And then we thought, like, what if we took that to the extreme? We take this kind of concept where we get all the good stuff, all the good isolation, and we really create a single shard per tenant, which could potentially mean millions of shards if we have millions of tenants. Again, some good stuff. We get the strict isolation, same as in the collection example, because a shard is a self-contained unit. It has its own storage. It has its own indexes. You get some of the resource isolation. You don't need to define the schema multiple times, because these shards, that's basically just an implementation detail now. It happens under the hood. You define your collection once, and then the shard belong to the same collection. So management is basically super, super simple. And my favorite point, the offboarding, it's very cheap and easy to do, because deleting a tenant is now deleting a shard. And again, this is basically just freeing a bit of memory, dropping some files on disk, and no longer has any kind of interference with existing stuff. But potential downsides. So this ring hashing that we just talked about, it just doesn't really make any more sense, because the whole point of the ring hashing is to map multiple keys or many, many keys to fewer shards. And then if you change the number of shards, you want to minimize data movement. So lots of data can stay where it is, and only very little data has to be moved. But onboarding new tenants, if you have millions of them, that's a very, very common operation. So we don't want to just minimize data movement. We need to eliminate data movement. Otherwise, this won't work. There is a potential for cost, so cost in the sense of resource cost, to explode, because now we have millions of shards. And if we have millions of them, like whatever cost a single shard has, now we have that times a million. And something that's also a risk factor is performance. So for example, when you're creating a new shard, is creating the millionth shard still as performant as creating the first shard? So it shouldn't degrade over time. So we said, let's do a couple of experiments and let's just see what happens. And surely it can't be that bad, right? So you can kind of imagine what the next couple of slides are probably going to be like. This was the first one. So we created an experiment with just 5,000 shards in our existing setup. And this is a super, super creative one that we didn't have on our mind at all. Weaviate is written in Go, and Go uses Go routines, which are lightweight threads. And they're meant to sort of not occupy physical threads when they're not currently doing something. Turns out, if Go routines are I/O blocked, they do actually occupy a physical thread, and we created 5,000 shards. 5,000 shards spawned their own background processes. All these background processes started to flush everything to disk at the same time, and all of a sudden we have 5,000. No idea why it exceeded 10,000 with just 5,000, so I guess there was some factor of 2 in there as well. And all of a sudden, those 10,000 Go routines actually required 10,000 physical shards, and the app just crashed. Very rare issue in Go. This is definitely one way to run into it. The cost part of it. So how expensive would it be? Well, for this same experiment, 5,000 shards, or slightly below, because we didn't want the app to crash, so we could still obtain the profile. That was 28 gigabytes. So that's 5.6 megabyte per shard, which means if we extrapolate to 1 million shards, that's 5.6 terabyte of memory. And that's basically for what is essentially empty containers. There's no data in those shards whatsoever right now. So it's visualized here by these empty glass containers. They're all empty, but they still take up a lot of time, because, a lot of space, because we have so many of them. Performance. 2 things in this graph that you definitely never want to see. One is, look at the graph sort of go up over time, so performance does degrade, it does go up. And then the second thing is we got these spikes where all of a sudden the P99 is 10x or so of the mean, which is also definitely not something that you want to do if you want to keep latency as a lazy. So again, we were at this point where we're kind of on the right track. Scaling through shards is good, but it really just shows that you can't do workarounds anymore. You really need something purpose-built to address multi-tenancy at the root. And this is where Weaviate 1.19 comes in. the first release to actually support native multi-tenancy natively. And quick API example, super, super easy to use. So first step, you just create a tenant, or you create multiple tenants in a batch if you like, and it's very, very simple. As part of your collection, you just specify the name of the tenants. In this case, it's tenant A. Similarly, if you create an object, same API as before, you just create the object, no need for a filter or anything, just specify the tenant name, in this case, tenant B. And then my favorite one, the deletion part, no need to like delete by query, delete by filter. You just drop the entire tenant by deleting it sort of as if it was a collection. The routing part got way simpler because we don't need the whole ring hashing anymore, because if we have a single tenant, a single shard per tenant, that's basically just a replicated lookup list. So in this example, tenant E, request comes in for tenant E. We know that tenant E is scheduled to node 2, and then if we're not node 2 ourselves, then all we do is basically forward the traffic to node 2, and node 2 can handle it. The size, we needed to make shards way more lightweight for this, and with the same 5,000 shards, memory footprint went down from like, I think it was 28 gigabytes before to just 870 megabytes, which is a mere 174 kilobytes per shard, which is pretty reasonable. So if we extrapolate that to the million example, that's 174 gigabytes, which I think still sounds like a kind of large number, but a million shards, so if you have 1,000 objects in your million shards, that's already a billion. If you have a million objects in your million shards, that's a trillion. So if for trillion scale vector search, 174 gigabytes of memory for overhead of shards, I think is pretty reasonable. So basically our like empty containers that took up lots of space turned into this like neatly stacked pack of Ziploc bags, which are like way more space efficient if they're empty than glass containers. The performance part, so this graphic is, or this chart is scaled in the same way previously, so you can easily compare it. And three good things. First of all, the mean latency is way lower. It's like at the bottom of the chart. It's constant. It no longer degrades. And we got rid of those spikes. So it's like pretty much a relatively smooth line, which is great. This is a screenshot from one of our automated load tests, like the Grafana dashboard that we have running for every release since we have the multi-tenancy test. I'm not sure if you can read the numbers, but this sort of imports 50 tenants at a time up until 120,000 tenants, and it creates, I believe, 1,000 objects per tenant, so that's 120 million objects. But it's not about the actual numbers. What it is about is the linear scaling of it. So if you would want to run this with, say, 240,000 tenants instead of 120,000, you would either add twice as many nodes, or you would use nodes that are twice as large. So the linear scalability is what we're trying to prove through that load test. Querying, of course, is also super important for a vector database. So the query part in here, you can see that at this time, about 3,000 tenants are currently queried with 16,000 or so queries per second at what I think is like a pretty reasonable latency, so that's kind of cool. Yeah, so far we've only talked about the scaling part, but we haven't talked about how we can actually reduce cost. And for this, we need to talk about storage a bit. So most vector search solutions out there typically run either entirely in memory or use some kind of a hybrid between memory and SSD drives. And memory is the fastest. No question. I mean, this is sort of ignoring CPU caches and stuff that's even faster than memory. But let's say for sake of argument, like at that size, memory is the fastest. And then cloud storage is like super cheap, but it's also kind of slow and like low throughput. And you have SSD drives that are somewhere in the middle. So it could either be like local SSD drives, local to the machine, or it could be network attached storage. One thing that we can do now that we could not do before, or that you definitely can't do if you don't have isolation per tenant, is the ability to deactivate tenants. So an active tenant is defined as a tenant that's already loaded into memory for whatever parts that need to be in memory and is ready to go, whereas an inactive tenant is currently not being used. It's like basically flushed to disk, but it only takes a few hundred milliseconds to activate it. So what you could do, for example, is if your app is UI-based and the user needs to log in, you could use the event of the user logging in, as a trigger to activate the shard. And because activating the shards, because they're pretty tiny, because we have one shard per tenant, is so fast that like a few hundred milliseconds in the context of how long a login takes, that's absolutely nothing. So you could even, like, when they start typing their password or something, you could activate it in the background and it would be absolutely ready by the time that they're logged into the application. And that means if at any given time you have only 20% of your tenants active, that also means that 80% are not active, and if they no longer have to be in memory, that's an 80% memory reduction right there, simply by not allocating resources for something that's currently not being used. So you're no longer paying for idle infrastructure, which I think is pretty good. We did also have cloud storage in here, so I think I also want to talk a bit about separation of storage and compute. Definitely a topic I think that we're going to hear more about in the context of vector search. Lots of stuff happening at Weaviate, also at other players, like looking into separation of storage and compute. And I think that could be its own talk right there. I only have one slide on it. But the multi-tenancy feature kind of sort of was one of the very, very easy ways to get started with a sort of architecture where storage and compute is separated. And the idea is basically that you make cloud storage the source of truth for your data. So you have some kind of an ingestion pipeline, and it actually first ingests into cloud storage or any kind of other kind of storage that's a source of truth. And then when a tenant gets activated, instead of sort of having it tightly coupled to a specific server, it's now, the servers are now stateless, and they just get a sort of temporary lease on that tenant to activate it. And then when querying is done or the user logs out again, it basically just returns it. And what that does is it makes the server stateless. And stateless servers are way, way easier to scale, of course, than stateful loads. So that's really, really good. So for example, for the kind of Black Friday case where all of a sudden, like, all of your tenants are active, but throughout a given year, yeah, most of them would not be active. So that's really cool. Right. So if you fell asleep 20 minutes ago and you still want to take something away from that talk, pay attention for the next 30 seconds. We sort of identified that most applications out there, whether they're doing retrieval augmented generation or search with vector search, do require multi-tenancy, as we could see from our sort of chatbot example where you have user spaces that you do need to separate. Multi-tenancy is hard. I hope I could get that across with all the sort of failed attempts and all the failed workarounds. And while you can do those workarounds to get started, it won't scale. Luckily, the scaling part is solved right now. You can use Weaviate's multi-tenancy solution, which can handle the scale and do it all efficiently. And then the coolest part about all of this is that not just do we overcome all of those challenges, but also new opportunities were created that maybe wouldn't be possible without multi-tenancy or without a dedicated multi-tenancy solution. So for example, the ability to reduce costs by deactivating tenants, the ability to go into stateless vector search, and all these kind of good things. Cool, that's it for me. You can connect with us at Weaviate.io. We also have a booth downstairs and a couple of people from the company, so please do come by and say hi. It's open source on GitHub, so Weaviate/Weaviate, and of course you can find us on X. It still sounds weird to say that. Find me at Etienne DI or Weaviate at Weaviate_IO. Thank you.